This video is part of a series aimed at people interested in using databases in their Unreal projects, focusing on SQLite. In the previous video, we looked at some basic examples of using SQLite databases with the plugins that ship with Unreal. In this part, we take a look at a free framework to make using SQLite databases easier. In the last video, we used some rudimentary code to access SQLite databases, utilizing the Epic plugins that ship with Unreal. By doing this, we realized that we need to clean up memory allocation after ourselves. There are only a few kinds of operation we need to make, repeatedly, and we need to loop over any result data and read out the values specifically, cell by cell. So let's get into this new framework of helper classes to make our database work simpler. I'll try to keep the latest source code for the framework on GitHub, along with the sample project I'll be using as an example in this video. The link will be in the video description. I'll also try to go through the Epic Marketplace submission process to make it easier for people who prefer to get their plugins that way. If I manage to get that sorted, I'll update the video description to say so. Things are slightly different depending if you include the plugin code directly or install via Marketplace. To include the source code directly, you need to place the folder in the plugins folder inside your projects folder, creating the plugins folder if you don't already have one. If you downloaded it from the Marketplace, then you need to add it to your project via the plugins menu option in the Unreal Editor. Regardless of how you include it in your project, you should be aware that it includes its own module with the SQLite core from Epic and an updated SQLite library code, so you don't want to include other SQLite plugins if you're using this framework. Using the framework, each SQLite database that you want to connect to is accessed through data access layer classes, which you make. Your data access layer class will either derive from UDBBase directly, which provides a basic set of functionality, or it will derive from a child class of UDBBase, such as USplitDBBase. You might also create your own UDBBase derived abstract base class if you have a specific way you want to use databases in multiple projects, or for multiple database connections in a single project. UDBBase and its derived base classes can be subclassed either in C++ or using blueprints, depending on your preference and needs. All the core functionality is provided to blueprint users, but as with most situations, C++ does give an extra breadth and flexibility just not possible with blueprints alone. Let's create a data access layer class, first with blueprints and then with C++. Create a new blueprint class. And choose UDBBase as its parent. I'll name it Tutorial Data Access Layer BP. And I'll click Save. These days I generally make my new Unreal classes from within Rider, but let's do it the old-fashioned way, for anyone using other IDEs like Visual Studio. I'll navigate to the project's C++ classes in the Content folder. Right-click and hit New C++ class. Select All Classes, and start typing UDBBase in the search. Select the class and hit Next. Let's give this one a similar name to the BP version, just without BP. So I'll call it Tutorial Data Access Layer. Click the Create Class button and wait for stuff to happen. What is it doing? Rider takes like 2 seconds to do this. Okay, I'll switch to the IDE and give the class a nice, pointless comment. Something which adds no more information than a person might get from looking at the name. Lovely. In the previous video, we added the Epic SQLite plugins and configured our project to use them. We created a content folder to store database files, and we configured the project to include them in the packaging process. Using the SQLite GameDB framework is very similar. Add the SQLite GameDB plugin to your project instead of the Epic SQLite plugins. Add a content folder for your database files, and configure the project settings to include your database files when you eventually package your game. Details on how to do this are in the previous video. Make a data access layer class for each database you want to connect to separately, either in C++ or in blueprints, and configure your project to use them. So how do we do that configuration? You can set this up once you've created your data access layer class, even before you add any functionality to it. Open the project settings and select the SQLite game database section. Enter the name of the content subfolder you set up for your database files. In my case, it's just called database. When the game starts up, Unreal creates an instance of the game instance database subsystem for us. This in turn is responsible for creating whatever database connections we tell it we need. We let it know what we want by creating database connection classes entries for each individual database we want a connection for. Click the plus button to add a database connection class entry. Select the DBase derived class that you've created in the derived class dropdown and type the file name of the database file in the content folder that you wish to use for this connection. The dropdown will only list instantiable DBase derived classes. Sometimes we want a single connection, but we will attach other database files to it during runtime. In those cases, we make the single connection and specify the additional files as attachments. Different UDB-based derived classes, such as the USplitDBbase, then get informed about these attachments when they start up and are able to use that information however they want. This in no way prevents you from making attachments to any SQLite database file you want by yourself. It's just a way to set up default values in the project settings. Okay, we're now ready to get things happening. Let's take a look at how we can use it. For these examples, I'll be using the sample Alien Warmonger DB database, and I'll include it with the code so you can see how everything works. If you want to know more about how database relationships work and see how I start to build the Alien Warmonger database as an example, I'll put a link to the video where I make it in the description and at the end of this video. Rather than just repeat the same thing for blueprints and then C++, I'm going to do two different examples. Firstly, using blueprints and widgets to make a very simplistic character creation process, and then a C++ example that will use a database to persist data across level loading. For the first example, we're going to use widgets and make a user interface that allows the player to select their character's class and background and displays which weapon types that class will be proficient with. We'll use the Blueprint Data Access Layer class we just made and add some functions to it to get the data we want. So, in our project settings under SQLite Game Database, we need to make sure we have a derived class entry that uses the Tutorial Data Access BP class and the Alien Warmonger DB from the database content folder. It's important to note you can only have one data access layer connected to any given database file. Otherwise, there would be a key violation and, more importantly, exclusive database access lock problems. In short, just don't do it. Anyway, before we do database stuff, let's create a user interface for our player to interact with. We need something to select the character's background and their class, and let the player enter a name for their character, a summary to confirm their choices and give any extra information. In this case, what weapon specialities they get from their specific choices. This is not a widget or UI tutorial, so I'll speed through this bit. And because I will be making selectable lists of things, I'll quickly whip up a clickable list item blueprint too. We now have an interface for the player to use. Nice. By necessity, the SQLite GameDB framework handles query results in a very generic way, with rows and fields, and each field has a number of value properties, one for each type of data the field could be holding. There are only actually 4 types with SQLite. It's generally up to the developer to know which type of data they expect from their query and read from the correct property. But the struct also provides a SQLite value type property, just called type in C++, which lets you know what the type returned from SQLite was, if you need it. It's perfectly fine to use it directly that way, but it's also a little nicer to transform the data into something specific to a given task, so that the data access layer returns or fills classes or structs that are more meaningful to the rest of the project. In this case, to keep things simple, I'm going to create just one struct and use it for everything we will be doing in this example. The struct is called Simple Data Item BP. I'll give it an integer ID, a string name and description, and a linear color called color. As I say, often you would create different structs or have separate classes for each thing, but in this case the data we'll be using is close enough to get away with having just one. You'll see what I mean and how that works. So the next thing we want to do is use our data access layer blueprint that we created and add functions to it to retrieve the data we want from the database. Because we derived it from UDB base, a query manager object is already set up for us, and the first thing we want to do is tell it to load the queries stored in the database. I'll do this right after the class is created by overriding the startup event, which is where data access layer blueprints can do any initialization they need. Calling load all queries into statements will read our queries from the database table that holds them and create wrapped, prepared statements for them, ready to use later. Because larger blueprints can get a bit messy with lines all over the place, I'm going to create a couple of support functions that will make the code a little cleaner and save repeating the same nodes in multiple places. Get query. It doesn't do much. It asks the query manager to return one of our prepared statements, given the query's name, and checks that the result is valid. That validity checking is more for packaged games, because non-shipping builds are set to throw an exception if the specified query isn't valid. That's intended to catch bad or missing queries during development, but it might become an optional setting later. Query result to simple array is an example of how we can turn our generic data returned by a query into something more specific that the data access layer can return to the rest of the project. In this case, an array of our simple data item BP struct. The function demonstrates that you can handle the data in various ways. The first 3 columns are always assumed to be an integer, a string name, and a string description, in that order. The framework also provides a utility function, color from database, which is used to return a linear color struct from 3 or 4 individual query result fields. It does not use the field order. Instead, it looks for field names that start with a specified root, in this case the word color, and end with R, G, B, and or A. If it finds them, it returns a color struct and a true Boolean value. If it can't find them, then a false Boolean value lets you know, and in this case, we'll use a black color instead. Similar helper functions are provided in the uGame database statics class, allowing you to make vectors and rotators from individual fields in the same way, as well as set an actor's location and rotation from database values. So, the actual functions that will return data to our project are get background list, get classes for background, get weapon types for character class. And additionally, we'll use one more function to save our players' choices back to the database, called save player info. The first 3 all look pretty similar, because they are. They each call a different select query, but in all 3 cases the results are turned into an array of simple data item BP. The things to note are, all 3 are called with execute result query. Get background list is the simplest, because it has no input parameters. In the case of the other 2, a call is made to bind parameter integer to set the correct value before executing the statement. Other than that, they all work in the same way. Get background list and get classes for background both return RGBA values, which are made into linear colors by the query result to simple array function. Get weapon types for character class returns no fields for color, so the function just defaults to black. Example blueprint data access class done. Right, let's start using our new data access layer class. I'll call the various functions from inside the game start UI BP widget code. To start with, let's create an initialize function. That's what our level blueprint will call after it creates the widget. And it'll pass in a reference to a skeletal mesh that I'll place in the level to give some sort of representation of the character to the player. So, it saves that reference into a variable and then calls the getDB function. Remember, a game instance database subsystem automatically creates an instance of any data access classes you've specified in your settings. In this case, we told it to create one of our tutorial data access BP classes and to use the alien warmonger DB in the database content folder. The getDB function calls getDatabase by file name, passing it the name of our database, which is used as a key to find the data access layer class, because there might be several. It checks that the object returned is valid before trying to cast it to our specific tutorial data access layer BP class. And if everything is okay, it saves the class into an alien warmonger DB reference for us to use later. The initialize function finally calls display backgrounds, which fills a scroll box with an item for each value returned from the data access layer get background list function, and it automatically selects the first item in the list. Selecting a background item automatically triggers the class items to be filled with the classes relating to the selected background ID, also provided by the data access layer function. Selecting a class item automatically retrieves a list of weapon proficiencies from the data access layer and updates the summary text with the information. This all ensures that when we open the widget, we always see a valid selection of values for everything. Whenever the background or class is changed, I use the colors we retrieved from the database to change one of the two material slots on the sample character mesh. In a similar way, you could just set clothing, base character mesh, attached weapons, things like that. A text edit box is provided for the player to enter a name for their character. The only code attached to that is to limit the maximum length of the character string. And finally, when the player clicks the accept button, the Save Player Info function in the data access layer is called, storing their specific selections back into the database. Making your game data-driven using a database in this way gives you the ability to more easily change certain things, simply by altering data in the database. Your queries can sort and filter data based on any criteria, and your data access layer can transform the query results into whatever structs you need or initialize classes with the specific data. The values are easily mutable and persistent if you want them to be. You could change colors, styles, mesh selection, etc. in the database during play, and see the results immediately and every time you subsequently played the game, or loaded a save. For the next example, we'll use the framework with C++. We're going to use the database to persist some actor-specific information between times when the player leaves and revisits levels. Let's take a look at the setup. We have 4 levels. In this case, I'm using level streaming and sublevels, but it's the same thing if you're manually loading individual levels, and the principle is pretty much the same if you wanted to use a technique like this for save game data. The levels I have are Start Room, Merchant Room, which would be some kind of shop with a counter, and 2 kind of corridors that connect these areas together, called Interchange 01 and Interchange 02. Those interchange levels are basically just used by the level streaming system to load and unload the other levels as the player moves along them. It's a pretty basic level streaming volume setup, and in our case it is a little bit contrived, created that way just to let us see the loading and unloading of levels and enable us to do something. The levels themselves have debug messages in their begin-end play events, so we can see when they're loaded and unloaded. And to make the code simpler and avoid needlessly repeating stuff we don't need to, all the sublevels derive their level script actor from a single level script actor class. That means they all share the same begin play and end play code. So let's run play and editor and check it out. The first thing we see when we start it up is that the persistent levels begin play fires, shown in orange, and then the begin play of the 3 sublevels which are initially loaded, the start room, and the 2 corridor interchange areas displayed in green. If we head to the left, we can see the interchange corridor 02 sublevel gets unloaded, shown in red, and when we come back, it is reloaded. Heading directly forward from where we start does the same with interchange corridor 01, and if we move all the way down this corridor, we see the start room is also unloaded, and the merchant room is streamed in. Running back to where we started does the reverse, unloading the merchant room and reloading the start room. In that start room, we have 5 instances of a simple AA actor derived class called a pickup item. This actor simply displays one of 5 different static meshes and allows the player to collect them. When a collision with the player is detected, the pickup item has 1 deducted from its quantity property. Items with a quantity of 0 are automatically hidden from view, and items with a quantity of more than 1 display the amount they currently have in their stack in a text render above the item. So the ammo clip and the banana have 5 and 4 items respectively in their stacks, and the other things only have 1. Running through them all deducts 1 from everything, and results in everything apart from the ammo clip and the banana becoming hidden. If we then run down the corridor towards the merchant room, the level streaming unloads the start room, and when we run back again and it reloads, we see all our items have reset themselves to their initial states. Of course, this is just an example, and sometimes this kind of behavior is exactly what you want to happen, but other times it isn't. For a more realistic player experience, sometimes you want certain actors in levels to be in the same state they were in when the player left them. Doors that remain unlocked and open, enemy NPCs that are unconscious or dead, stashes that have already been looted, etc. And this is where our database comes in. Let's add a few things to the empty data access class we made earlier in C++. Firstly, I'm going to override the build method so we can do some initialization, similar to what we did with the blueprint data access layer class. In this case, I'm adding just one thing: query manager load statements. This means when the class is initialized, it will automatically look for saved queries in the database and make prepared statements from them. Then I'll add a few functions that will call those database queries. IsLevelManaged will give us a Boolean result, letting us know if a particular level or sublevel's name is found in our database's level table. GetLevelID goes one step further, returning the actual level ID integer number from the database, or a -1 if the name isn't found. So yes, effectively, GetLevelID could be used to perform the same function as IsLevelManaged, but the queries and the return values are slightly different, and I wanted to give both as examples. Then we have two functions, one to save the current state of our pickup item actor, and another to load it back in. I've tried to keep these things simple by showing only one value which is persisted and retrieved from the database, a quantity. But in many cases you want to persist several properties at once, and that's perfectly fine. Later we'll take a look at some additional helper functions that assist in storing an actor's location and rotation, but for now quantity will demonstrate the basic functionality. Next, I add two functions to the pickup item class itself: SaveState and LoadState. These functions will call our data access layer functions, and themselves they know nothing specific to the database. I also added a Boolean dirty flag to the class, which is set true whenever any of the persisted properties are changed. In this case, that's just quantity for now. This allows the SaveState function to do nothing if it knows that no data has actually been changed. So when do we actually call these functions? In this example, I'm going to call them when each sublevel is loaded or unloaded. Depending on the specifics of your game and how everything is set up, you could actually do it when each individual property is changed. Saving the value for a single item as it changes might be more performant for you than saving them all up and doing it when a level is unloaded. It really depends how your game is going to work, how many items you will have, and how many properties you want to persist, as to which method you might want to choose. You might choose to perform batched save loads on a separate thread while the player continues to play, or you could wait until you perform either an automatic or manual save to do it. My level script actor derived class is a convenient place to know when the sublevels are loaded and unloaded, because all the sublevels use it, and it overrides begin play and end play. When begin play happens, I get the name of the sublevel and I list all my pickup item classes. I loop over them, using only ones that are in the current sublevel by comparing the actor's level name with the sublevel's name. If I get a match, then I call the data access layer method and try to load a value from the database. If a record is found for the item ID and level ID combination, then that value is returned and we set the item's quantity property to that value. If, however, there is no record in the database for this item, then the query will return a value of -1, in which case we don't set the quantity. We leave it with whatever value it currently has. That will either be the default amount of 1 set in the C++ header code, or an amount that was manually entered for the item in the editor. It is worth noting here that our database table which stores this data has a composite primary key, meaning a primary key made of several fields which taken together give a unique value. We do this because we use the name of the actor item, and by itself that wouldn't be enough. Several different levels might, and probably would if you leave the default names for items, have instances of actors with the same names. But as the actor's name is unique within a specific level, we combine it with our level ID, and that gives us the uniqueness we need. So, having made the appropriate changes, let's run the game in the editor again and see what happens. Everything looks the same as before, which is what we would expect. Any attempt to load values for our items will have failed with a -1 return value, because currently we don't have any data for them in the database yet. So let's make some. The character will move over all the items just as before. and then run down the corridor, which unloaded the sublevel and triggered the saved methods, creating a line of data in the database for each item. This time, when we return to the start room, we can see the items are exactly as we left them. And if we exit Play in Editor and restart it again, we see the same thing. The values which were saved to the database have automatically been loaded when the sublevel begins play, and the items are appropriately reinitialized with those values. Taking a look at the data in the database table shows us pretty much what we would expect. A record has been created for each pickup item, and the quantity value has been set to the appropriate amount. You can also see there are a number of other fields in that table for storing an actor's location and rotation. I'll cover that in another video. Hopefully, this gives you an idea of what we can do with the database and how we can simplify some things compared to using the default SQLite classes that ship with Unreal on their own, by using this framework to provide some useful additional functions and simplify repetitive tasks. The next video in this series will go back to basics and look at how we actually design the relational databases that we use for our games, different types of relationships and how we might use them, and take a look at writing SQL queries to perform some basic database operations.